Hello everyone, I am C. Kavita from SRM Engineering College. Now I am going to speak about wide bandgap devices and its application. And you can see that the wide bandgap semiconductors are a special type of semiconducting material that help us in our day-to-day life. So the special kind that I have mentioned is due to the bandgap energy level. So as you see, the different semiconducting materials are compared. So we know that conventional semiconducting materials like germanium and silicon, they are usually used and they have a energy bandgap energy of 0.7 and 1.1 respectively. And this bandgap is nothing but the gap that is energy required for the conduction of the semiconducting materials. So this bandgap energy should be more for a special kind of applications. Also, this can be seen in gallium arsenide, silicon carbide, zinc oxide, gallium arsenide, and diamond. So these material have very high energy bandgap, uh, and this can be used for special applications. So what is band gap and why it is so important? So band gap is nothing but the energy that is required to excite an electron from the valence band to the conduction band. So this energy must be adequate to uh, agitate the electron to move from valence band and conduction band. Hence the conduction of the electron is happening and we can get the current from that. So if the band gap is very large, then a critical high electrical field will be very high in order to initiate the impact ionization. So this may cause a very huge avalanche breakdown. So these devices have very high reverse voltage withstanding capability. So this is the main advantage, and also the breakdown voltage is 1 by 2 of the drift width and critical electric field. So for the same breakdown voltage, you can expect the wide bandgap devices to be very smaller. So this thing that we have achieved is used as advantage. So due to the large bandwidth band gap energy, very high temperature is required to cause the ionization. So this thing is also used as an advantage. So very high temperature operation is also possible. So these two things, that is size is smaller and very high temperature operation is possible. So these two things for very high critical electric field can be used for specific applications. So this is what the very high bandwidth devices are potentially helpful in. So the different parameters that is compared here is based on the different semiconducting materials like silicon, gallium nitride and silicon carbide. So in silicon, as we know, it is a very common or conventional method, conventional semiconducting material. So when you see the band gap in terms of electron volt, you can see 1.212 is the band gap. For gallium nitride it is 3.39 and for silicon carbide it is 3.26. So you can see a very high band gap energy that is required for conduction. So hence the critical field that is seen as 0.23 for silicon and 3.3 for gallium nitride and 2.2 for silicon carbide. So hence the electron mobility is also, you can see that 1400 for silicon, 1500 for gallium nitride and 950 centimeter square per volt second is for silicon carbide. So hence the permittivity is compared, then thermal conductivity is also compared. The main objective is we can use in very high temperature environment and we can use for very high voltage systems, electric conversions and power conversions. The very high power conversions are mostly reliable on these kind of special semiconductors. So we can see that gallium nitride So this gallium nitride is a special material that is a reliable future in power conversion. So in power conversion, we have to opt for a very special material that is, as we know that the power conversion is very critical thing nowadays, and we are more relying on the renewable sources. But gallium nitride and silicon carbide is a new technology that is helping us in having a very huge performance with less cost. So renewable energy sources are uh, useful, like solar, wind energy, that are useful, but their cost is not that so high, that I mean affordable. So we are going for this gallium nitride and silicon carbide. So what are all the aspects of energy saving and carbon footprints? So we can see that wide bandgap semiconductors purely is based on energy saving, and it can save up to $15 trillion, which is equivalent to around about 15 lakh crore rupees, when we use wide bandgap semiconductor instead of going for some renewable source or else non-renewable sources as we use now. So wide bandgap semiconductors based power electronic system can mostly reduce the cost, and we can save up to 15 lakh crore rupees. So this is a huge number. Uh, so so this is the impact of wide band gap semiconductors, and the cumulative impact of this technology in 20 years can also reduce the carbon dioxide emission by 2 trillion pounds, which is the total of carbon dioxide emission in the world for 2 years. So if you consolidate it for 20 years, this usage of wide band gap semiconductor can reduce the emission of carbon dioxide also. So in that way also we are helping the environment to go forward. So this is what we are going to see with the help of this wide band gap devices. So if you see the impact on solar, so what kind of impact we have solar? So wide band gap inverters that converts DC to AC is also a very huge technology. So initially we are going to convert the solar into DC, and then that DC is converted into AC with the help of this wide band gap device. So we can cooperatively work with the renewable resources to obtain furthermore decrease in the losses by 50%. So this is the main power train of the Tesla's electric car. You can see it is very huge. So in future and also in Toyota you can see that the plug-in chargers that are very huge in size, and you can reduce the size by 10x time. That reduce the size by 10x time, which also includes the reduction by 10x time in the cost. So cost as well as size for the EV, that is electrical vehicles, for a Toyota as well as for Tesla, can be reduced with the help of silicon carbide high frequency charger in the next generation. The wide band gap material cut the electricity losses that happens during charging by 66%. That is also added advantage of the wide band gap devices. So so next is the thing that is going to change is size. So weight is reduced, and also the power that is being delivered is that Toyota charger can deliver up to 1 kilowatt, but the silicon carbide chargers, EV charger, can deliver up more than 6 kilowatt. So this is the main difference in the charger. So you can see that comparison, the volume is reduced by 6 folds, weight that is 6.6 kg, but our prototype is having only 1.165 kilogram, and power that is delivered by the particular technology is like Toyota baseline is 1 kilowatt. For our wide band gap devices give up to 6.3 kilowatt, and efficiency is lesser than 90%, whereas we can expect somewhere up to 95.1. So these are all the research outcomes that have been done, but if if you are commercializing and if you are going to implement it in the near future, we can expect a very good improvement in the technology. So LED is your wireless wide bandgap device based LED can produce 10 times more light, and also it can last up to 30 times longer when compared with the conventional technologies. And also if you see, you can use in all the day-to-day life technology, that is day-to-day life devices like AC, fridge, washing machine, fan and stoves and charger. So HVDC system that is used for providing power is also proposed to have wide bandgap devices. So this increase the energy efficiency in the areas like industrial motor system, consumer electrical and data centers, and conversion of solar and wind energy. So industrial motor system is having more current saving opportunities, and consumable electronics and data centers is also having like 1.7 million homes benefited, and also conversion of solar and wind energy can have up to 7,50,000 homes benefited. So that can be done with the help of this particular technology. So these are all the references. These are all the references you can have. So thank you. So once this technology is very suitable for the near future, and I expect the students to learn this and implement in your research and development as well as in your current future.